Hello. So in this section, we're going to talk about the definite integral. So let's say that we're considering a function defined from a to b, and we want to find the area that lies beneath it. So we're integrating from a to b of f of x dx. Now, the thing of which that you'll learn in this section is that we can basically find the definite integral from a to b for f of x dx if we take the limit as n tends to infinity for the series sum from k equals 1 to n of f of xk star times delta xk. Now, delta xk is basically defined as b minus a divided by n. Now, xk star is actually just a point that lives inside the xk minus 1 comma xk interval. So in this case, like all that we're doing is we're just going to go ahead and add a bunch of rectangles as follows, because we can inscribe as many rectangles as needed into this region until we basically fit as many as we can until it forms the true area. So what we kind of mentioned before is that the point of which that we choose um, for the height to be technically does not matter. So what we're going to do is we're just going to look at what we call the definite integral. So to look at the definite integral, I actually need to establish that basically the definite integral is only calculating the net area. Okay, so just make sure that you understand that you're only calculating the net area, which means that if you want to find the total area, you just need to use the absolute value. So here are some properties of the definite integral. So if you integrate from a to a of f of x dx, well, there's no area to actually integrate, so that's just going to be 0. If we integrate from a to b f of x dx, and we actually reverse the process of the integration, so like we do like this, we just basically just make it negative to account for that. Now, the next thing that we have is that if we are integrating from a region a to b f of x dx, we have that essentially we can partition it into several integrals over the interval. So we have this would be from c to b, and then that's f of x dx. Now, there is another property that we can add in, and that's basically if we are integrating from a to b of f of x dx, so we'll just do f of x plus or minus g of x, and we'll close it. Basically, we have that we can separate these. So we have that that'll be a to b f of x dx, and we'll just put plus or minus integral from a to b g of x dx. So these are the properties mostly that you'll need. So we have 1, 2, 3, 4, and let's see. Okay, so we have 0 partitions. Oh, okay. Yeah, there's actually another, and that's if we integrate from a to b, and then we take some constant k, multiply it by f of x dx, this constant comes out. So we have that that'll just be k times the integral from a to b of f of x dx. So constants can come out. The other is that basically you could have that if you're integrating from a to b of the absolute value of f of x dx, this is basically just the total area um, in this case. Now, let's go ahead and look at some examples of geometry. So when we talk about area, it is possible that you might have regions of which represent kind of like shapes that you're familiar with. So we know that the area of a circle is pi r squared. We know that if we have a rectangle, that the area is just length times width. We also know that if we have, let's say, a triangle, that the area is base times height divided by 2. But furthermore, we also have that if you have a trapezoid, for example, like if you have, so if you have something, um, hold on. Yeah, so let's say that we have a trapezoid, and we'll just do it like that. Okay, now accordingly, it's going to be the two bases multiplied by the height and then divide by 2. Now, mostly, you know, if you were to, let's say, for example, have that you have the integral from 0 to 3 of, let's say, like 9 minus x squared dx, not that actually. We'll say, like, for example, like you have the square root of 9 minus x squared dx. Well, if you look at the region in question, you'll notice that basically it just represents a quarter of the area. So in that case, you know that it's pi r squared divided by 4, which in this case would just be 9 pi over 4. Of course, like if it was the whole circle, then in that case, you know that it would be just 9 pi. But if it was half of it, then it would be 9 pi over 2 and so on. Now, interestingly enough, the trapezoid is very useful. And I'll just put like a little, you know, curve like this. So let's say that, for example, that you have that you pick a point right here and you pick a point right there. Well, you can actually form a trapezoid underneath it. So in that case, notice that this would be the area of that ith trapezoid, and if you keep doing that over the entire interval, it's theoretically going to be more accurate. So again, this is something from Cal 2, but you know, if you want to get ahead, basically it's just taking the lower sum plus the right sum and then dividing by 2. You'll learn more efficient methods, but for now, you know, we'll just stick to these nice little geometrical formulas if the region happens to represent any of these. Now, what I want to look at though um, is, for example, let's say that we want to find the integral from 0 to 4 for 3x squared dx. What I can do what I can do is basically just say that, well, we can go ahead and find the definite integral by by partitioning this. So we have that, let's say that we have delta x. So delta x is 4 minus 0 divided by n, so that's going to be 4 over n. Now from here, all that we need to do here is say that, well, we need to find what f of xk star is multiplied by delta x. Now, in my case, I'm actually going to say that xk star is equal to the right endpoint. So we're going to have 0 plus k multiplied by 4 over n. So that's going to be, it sounds weird, but 4k over n. Now, what that means is that basically you have 3 multiplied by 4k over n, and that's squared, but then that's multiplied by 4 over n. Now, basically, when you simplify this, this is going to be, let's see, we have 1664, so this is going to be like 192. So we have 192 over n, and then that's going to be k squared. Okay, now, um, let's see, anything else that we need? Not really, because I got, this is supposed to be n cubed, actually. Okay, so what we're going to do is we're just going to say that we have the summation from k equals 1 to n of, okay, so we went ahead and we multiplied through, so we got 1664, and then yeah, we said 192, so it's 192 over n cubed, and then this is k squared. Now, what this is going to give me is 192 over n cubed, and then we have the summation of k squared from n equals 1 to n, or not n, but k. Now, we have that basically this tells us, furthermore, that this is going to be 192 divided by n cubed, and then this is going to be, okay, so we actually know what k squared is. It's n times n plus 1 multiplied by 2n plus 1, and then this is all divided by 6. Now, notice that, for example, that we can actually simplify this even further. Because, for instance, we have that 192 divided by 6 is 32. So this is going to be 32 divided by n squared multiplied by n plus 1 times 2n plus 1. But then let's go ahead and distribute the n plus 1. So we have, this is going to be 2n squared plus 2n plus n plus 1. And basically, when we distribute this, we're going to get 64 plus, okay, now technically that's going to be 3n, so that's going to be plus 3 over n plus 1 over n squared. Actually, that should be 32. Actually, this is all wrong in terms of the numerator. So that should be 32, not 32, but 64. So this should be 64 also. Hang on. Let's see. That should be 3, so that's times that should be 96. Okay, sorry. So that should be 96, and then that should be 32. So let's just write 32. Now, it's not very important, but if we want to be accurate, then yeah, we'll have to use this. Now, notice that basically we're saying that if we take the limit as n approaches infinity of 64 plus 96 divided by n plus 32 over n squared, that this is going to equal to 64. But this is going to be 64 units squared. So that's it, 64 units squared. So this whole process basically showed me like how to find the definite integral for this. Now, usually in class, I'll always ask, well, what exactly is this right here? And the answer is basically this represents the error. And our idea is that we just want to minimize that, okay? Now, if you want to basically apply, like say for example, you want to just use like that you want to just find the area of a region. So like let's say like you have the area of 2x plus 3 dx. Technically you can apply this method, but you really don't have to. Why? Because if you go ahead and you graph this, you'll see that you'll have, okay, well, this will be 7, and then when you plug in 4 you'll get 11. So maybe like this. So you'll have that you have a point right here. So maybe this is 2, and then maybe this right here is 4. So then this right here is 11. So in this case you have that the region looks something like this. Okay, now notice that the region is completely bounded below, like so. And to do this, all that we need to do is just figure out like what's the heights respectively. So essentially we have that this is going to be that the area is going to be 2 multiplied by 7 plus 1, but all of this is divided by 2, which in this case, this gives us 18. 18 what? 18 units squared. So notice that using geometry was actually pretty useful because we could just say, okay, yeah, that's just 18 units squared. Now, I would recommend that you do try to show that the integral from 2 to 4 of 2x plus 3 dx is equal to 18. But that's using that method, for instance. So one thing that you are going to learn is that, when you find the area or the integral from 2 to 4, you're going to notice that it's x squared from 2 to 4, and then plus 3x from 2 to 4, of which this is just going to give you 16 minus 4 plus 6. Yeah, plus 6, which is equal still to 18 units squared. So as you kind of do these problems, you'll kind of notice that you have your own preferred way of doing it. You can either use the Riemann sum, or you can use geometry, or you can use the antiderivative. This right here was the this right here. This was actually me using the fundamental theorem of calculus, which is the next section. So yeah, this right here is equal to that. But note that, if you did try to use the Riemann sum, you would have ended up saying that delta x is equal to 2 over n. Then from there, you would have had to figure out, like, for example, what is the best point to choose. At this level, it technically doesn't matter. because like you would say that xk star is equal to 2 plus um, maybe like k times 2 over n, and then this would be 2 um, 2 plus 2k over n. Now, this isn't really that difficult in that sense because you could probably argue that you don't really need to consider the 2 technically, nor do you even need to consider the 3 because they're just constants. But that's like another discussion that, we can talk about, like as it relates to, shortcuts and whatnot. Um, so try to look at, whichever methods that you would prefer. But for the most part, as long as you kind of have the idea of how are you finding definite integrals, then it's all the same really. Um, okay, so as long as you can show that it is definitely a limit, then it's all fine. But once you get to the fundamental theorem, you'll probably never do this again.